Welcome to this e-lecture, which will be about bivariate regression analysis. And what is bivariate regression analysis? What's the purpose of bivariate regression analysis? Well, it's to describe a relationship between two variables as a linear relationship. And we interpret the effect of the independent variable on the dependent variable as a mean change in the dependent variable when units have higher value on the independent variable. And we are interested in finding out whether there's a mean increase in the dependent variable when units have a higher value on the independent variables. Thus, is there a positive relationship, or is there a decrease in the dependent variable when units have a higher value on the independent variable? Thus, there is a negative relationship. And we are also interested in examine how much of the variation in the dependent variable that co-varies with the independent variable. So we are interested in knowing how much of the variation in the dependent variable is explained by the independent variable. And we want to find out whether the relationship can be generalized from the sample to the population. This is inferential statistics. And whether there's a causal relationship between the variable is likely or not. And that's more into multiple regression analysis, which will not be a part of this lecture. But okay, we want to find the function for the linear relationship. And here I've illustrated the regression, the function or the equation for the regression line, where y is the dependent variable and a is the constant. That is the value on the dependent variable y when the independent variable x equals 0. And b is the regression coefficient. That is the change in the dependent variable y when the independent variable x increases with one value unit. So if this one is 0, then this whole part falls away. So then you're just left with the constant. So yeah, and this says something about the change in the dependent variable when with 1 unit's increase in x. So you can see it here. When x is 0, then you have the value on the y is equals a. But when you have 1 unit's increase in x, the increase in y, there's also an increase in y, and that increase equals b. Let's see how this is all how this is all the computation of it all. We use ordinary least square to find the regression line with the minimum variation. That is is to minimize the sum of the squared errors or the unexplained sum of squares to find the line that best fits the data. And this is the equation for ordinary least square. So we square the deviations from the regression line. The square deviation from the regression line are minimized. So large deviations are more important than smaller deviations. And let's look at a more hands-on example. We have a scatter plot. This is a scatter plot between life expectancy in 2011 and the government's share of health expenditures for 191 countries, and we want to fit a line to this data, line that fits the data the best way possible, and where the deviations between these plots and the line is as small as possible. That's really our goal, and we know that the mean on the government's share of health expenditures is 59.4%. So if you have x with a bar over it, that's the mean on the x variable, and the y with a bar over it, that's the mean on the dependent variable, which is life expectancy, and that's 70 years. But we want to fit a line to this data, the regression line, and the regression line looks like this. This is the best fit to this data, using government share of health expenditures as the dependent variable and life expectancy as the government share of health expenditures as the independent variable and life expectancy as a dependent variable. So this line is based on this regression equation. So when x is 0, or the constant, then a is 58.4 years. So we start at 58.4 years, but that's only technical interpretation, because as you can see, there are no countries where you have where the government's share of the health expenditures is 0. So that's only a technical interpretation. And 0.2, that's how much the life expectancy increase when you have 1% increase in the government's share of health expenditures. But let's look at the interpretation more using the regression equation. So yeah, 58.36 or 4 then is the constant, which is the value on the dependent variable y, when the independent variable x equals 0. So that's average life expectancy when the government's share of the health expenditures equals 0. But again, that can only be given a technical interpretation, because there are no countries where the government's share of the health expenditures are equal to 0. So really, if you are going to interpret the constant, give a meaningful interpretation of the constant, 0 has to be a substantial value on or some of the units. You have to 0 has to be a possible value in the data, and in this case it's not. There are no countries where it equals 0. And the regression coefficient, that's a change in the dependent variable y when the independent variable x increases with 1 value unit, and average life expectancy increases by 0.2 years for each percentage point higher the government's share of health expenditures. So yeah, that's the interpretation of the regression coefficient, and this equation is our best fit to the data just presented, and it's the bivariate it's based on bivariate regression analysis, where we want to fit a linear relationship between the data. So that was the e-lecture on bivariate regression analysis. Thank you so much.